Stephen Hawking demonstrated that black holes eventually evaporate by emitting thermal radiation. If a black hole evaporates completely, the rules of quantum mechanics dictate that information cannot be destroyed, requiring that all data that fell into the black hole must eventually escape in that radiation. This creates a strict mathematical conflict. For information to be preserved, a late-time Hawking particle must be quantumly entangled with the early radiation. Yet, local quantum field theory demands this exact same particle must also be perfectly entangled with its partner falling into the black hole interior. Quantum mechanics strictly forbids this kind of perfect three-way monogamy. Resolving this entanglement conflict requires breaking a core pillar of physics. If we enforce unitarity, the entanglement across the event horizon must break. Severing that connection tears the smooth geometry of spacetime, generating a localized wall of high-energy quanta, an Amps firewall, right where the equivalence principle says an infaller should notice nothing at all. Theorists have attempted to bypass this with alternative frameworks. The ER equals EPR hypothesis proposes that entanglement creates actual wormholes, but this requires highly complex, non-trivial connectivity in the bulk of spacetime. The soft hair proposal adds physical charges to the horizon, but it fails to specify a distinct transport mechanism to get the information out. Both of those approaches collide with the strict constraint of topological censorship. Classical theorems forbid macroscopic bulk topology changes from being observable to any asymptotically flat observer. A viable solution to the information paradox must therefore preserve standard unitarity and allow smooth infall, while leaving the classical bulk topology of the black hole entirely unmodified. Researcher Ido Margolin proposes a strictly topological modification to the event horizon itself. His thesis posits that at quantum scales, the horizon is effectively non-orientable. This model imposes an orientation-reversing crosscap on the boundary of the stretched horizon. This boundary condition makes the geometric factorization between interior and exterior purely conventional. Quantum information strictly lives on a single two-dimensional manifold containing a permanent parity twist. Redefining the boundary algebra in this way bypasses the need for bulk transport channels entirely. Without the need to physically transport particles across the threshold, the local conditions that generate firewalls are preempted. This equation shows the modified Bekenstein-Hawking entropy calculation, introducing a topological contribution to the area law. The multiplier, the Klein index, is 1 plus delta K, representing the parity twist density across the horizon. For standard orientable horizons, delta K is 0, strictly recovering Hawking's thermodynamic law. Delta K is not a localized variable. It is a universal topological factor extracted directly from the boundary partition functions, calculated on the non-orientable Klein-Bottle geometry. To calculate this, the stretched horizon area is geometrically split into highly regulated ultraviolet patches. The model operates on the membrane assumption. It replaces the standard orientable patch with a non-orientable crosscap identification, specifically at a structural thickness approximately equal to the Planck length. By calculating the overlaps of these crosscaps, small departures in delta K capture the soft, parity-twisted corrections to the horizon's entropy. This index functions as a finite topological renormalization of the area law. It does not introduce any new local degrees of freedom into the physics. The macroscopic state counting mathematically absorbs the parity-twisted sector. This allows the system to hold quantum information globally without altering the local Hawking thermodynamic limits. Any valid resolution to the information paradox carries a rigorous requirement. The quantum state near the horizon must remain Hadamard. This ensures smooth infall for an observer crossing the threshold. This maps the twisted correlator equation, separating local experience from global state. On the left, local Hawking physics and thermal conditions remain unchanged. The infaller's horizon is normal. On the right, global cross-horizon operators follow an orientation-reversing automorphism, mathematically mirroring the interior and exterior. Because of this mirror relation, the cross-horizon mutual information acquires a parity-twisted component that scales linearly with delta K. Since the delta K term operates purely as a global boundary automorphism, it strictly preserves the Hadamard short distance form required for empty space. By moving the entanglement structure into a global parity twist, the local monogamy conflict is eliminated. The framework preserves unitarity, and because no local firewall is induced, it protects the equivalence principle. Moving this framework from conformal field theory into reality requires strict empirical falsifiability. That transition relies on analog gravity experiments. The proposed 2026 experiment uses a Bose-Einstein condensate. This physical laboratory setup forces a ring or elongated condensate to cool to extreme nanokelvin temperatures. This visualization illustrates the creation of a sonic event horizon. It forms via a strict flow transition, pushing the condensate from supersonic to subsonic velocity. To test the proposal, physicists engineer twisted boundary conditions into the fluid. They apply an orientation-reversing phase using synthetic gauge yields or Raman coupling. This induces a spatial parity flip, strictly on a thin membrane region of the fluid, directly mimicking the boundary conditions of Margoline's stretched horizon. The experimental measurement target is highly specific. Probes record the density-density correlations and entanglement witnesses between the exterior and interior sections of the flow. This BEC architecture provides a mathematically precise, highly controllable analog. It tests the parity twist entropy hypothesis natively, observing how information behaves across a boundary. The experiment requires a verified baseline. The control setup must first accurately reproduce the standard, orientable analog Hawking partner stripes to prove the sonic horizon is functioning. This matrix establishes rigid acceptance criteria to distinguish the non-orientable hypothesis. The primary requirement is detecting a parity-twisted component in pair correlations that scales linearly with delta K. To prevent false positives, reversing the synthetic field must flip this signature sign, leaving standard controls unchanged. The proposal establishes a definitive falsifiability threshold. If there is a complete absence of a twist-induced cross-horizon signature above a strict noise floor of 10 to the -2, the hypothesis fails. Unlike frameworks that retreat into unobservable holographic dualities, the Klein horizon boundary proposal forces quantum gravity theories out of the abstract. It demands they survive concrete, near-term experimentation.